Okay, here's another picture. Here's your RC circuit. This is the behavior of the AC circuit. If you have an AC source, this would be the behavior if you have a square wave. In the RC circuit, current reaches zero before the voltage does, so that you have this relationship, this phase relationship between the current and the voltage. Very similar to this one, we're just at a different point in our rotation, our continuing rotation around the reference circle. Now up here, first of all, let's consider what happens if you have an inductor instead of a capacitor here, driving it with an AC source. Okay, the voltage produced by the inductor also opposes the increase in current, but it opposes it in such a way that the inductor voltage is going to be proportional to the derivative of the current, the rate at which the current is changing, because the changing current is what changes the flux, and the changing flux is what creates the opposing magnetic field, or the magnetic field that creates a voltage that opposes the increase. So it follows then that the voltage of the inductor is going to be zero whenever the derivative, or the rate of change of the current, is zero, and that occurs when the current is a max or a min. Is very, just think of max and min in calculus. They occur when the derivative is zero, and again, that's exactly when the inductor voltage is going to be zero. So I is maximum or minimum, which implies that I is going to hit zero after the source voltage hits zero. And we think about why that's the case, and we could draw it out and analyze it, but we're not going to take the time right now, and that's something I really kind of want you to think about. So the idea, though, is very clearly, by this line of reasoning, the inductor voltage is going to hit zero before the current hits zero, so that the current in an LRC circuit is going to precede the inductor voltage, is going to follow the inductor voltage. The current is going to hit zero after the inductor voltage hits zero, and that would be the case in this picture. The inductor voltage is going to hit zero when the inductor voltage vector is vertical. Now, if you have a circuit with an inductor and a capacitor, then the voltage of the capacitor will lag the current. The voltage of the inductor will precede the current, and the resultant voltage of the inductor and the capacitor is going to be just the resultant of these two vectors. Now, we haven't seen the expressions, we haven't derived the expressions for the magnitude of this voltage compared to the current, or the magnitude of this voltage compared to the current, but they can change. So this vector might be much longer, this vector might be much shorter, or this vector might be longer and this vector shorter, in a way that we'll see soon. So that this resultant voltage could end up preceding or following the current. Or it could be that these things just match up in such a way that the resultant of these two voltages is in phase with the current, in which case we'd have something we call resonance. Now, if there's a resistor as well, and let's label this V-res could be read as resultant. Okay? So resultant voltage vector. And now I've lost my train. Oh yeah, if there's a resistor in here, because I had to label that so it wouldn't look like voltage of the resistor, then the voltage across the resistor is in phase with the current, because the voltage of the resistor is just voltage times current. There's no phase lag involved. So you would have another vector parallel to the I vector, and you would have to take the resultant of all three vectors in order to see what's going on in the circuit. Now, we haven't again, we don't know yet how to determine the relative magnitudes of VC and VL and VR if there's a resistance. But we understand that we can use this kind of a diagram to visualize how the voltage either precedes or follows the current. And that's the essence of the phasor diagram. We just need to work through the details of how to find these magnitudes and the angles between these voltages and the current.